So in this next video, we're going to be talking about trigonometric integrals. So trigonometric integrals. And these are usually integrals of the form so they're usually the integrals of the form sine x, sine to some power x, cosine to some power x. So there's usually sine and cosine. Then we also have forms of integrals where we include tangent, m, secant, and x, and there's also one for cotangent. But to solve each of these integrals, there's a slightly different process. So these are just the cases. So let's say this is case A, case B, case C, right? So starting off, we'll just start with case A first. Let's just make a line here. So let's just start with case A with the sine and cosine. So in order to solve for sine an integral of this type, we're gonna need there's gonna be two cases. There's two cases within this general integral. So whenever we have odd powers and whenever we have even powers, those help us determine if we're gonna have to use Pythagorean identities or half angle identities. So what I'm gonna do is write sine, right? So whenever we have odd powers and whenever we have even powers, right? And whenever we have odd powers, we use the Pythagorean identities, right? Now for even powers, we use the half angle identities. So these identities, we're going to be substituting them in the integral so we can simplify it a little. So let's look at the odd powers case first. So let's say m or n, right? M and or n, right? Both could be odd too. M and or n is odd, right? So this is one of the cases. And whenever we have odd powers, we have to see if it's on the sine or the cosine. If odd power is of sine, right? If sine has the odd power, what we want to do is keep one factor of sine and use the Pythagorean identity, sine squared x minus 1 minus cosine x, 1 minus cosine squared x, right? Use the Pythagorean identity. And that identity is sine squared x equal to 1 minus cosine squared x. So that's if sine has the odd power. But if cosine what we have to do is keep one factor of cosine, right? And use the Pythagorean identity cosine squared x is equal to 1 minus sine squared x. So if cosine has the odd power, we use the identity for cosine. Right? So in this right now, I just explained if either one has a power, an odd power. But what if both of them have odd powers, right? And if both have odd powers, just pick one method. Just pick one method, right? And just pick one method and just make sure you get at least a power of 2 on either sine or cosine, so you can be able to substitute the Pythagorean identity. So this is the first case, right? When m or n is odd. The second case is, so let me actually move all of this to the next page so everything is together. So I'll just put this like right here. So there you go. And the second case is where it's even. So m and or n is even. So if both powers are even, if one of them or both of them are even, we can actually use the half angle identities. So actually it says if both powers are even, use the half angle identities. So the half angle identities are as listed, right? I'll write it right here. Sine squared x is equal to 1/2 1 minus cosine 2x. That's for sine squared. For cosine squared x, the half angle identity is 1/2 1 plus cosine 2x. Just like that. And say if we have sine x times cosine x, sine x times cosine x, and this is the case we're going to use when both of them are even, is equal to 1/2 sine 2x. So these are the half angle identities. So whenever you have odd powers, we're going to be looking at the Pythagorean identities. Whenever we have even powers, we're going to use the half angle identities. So let's do like a few examples of this form of integral, this case one. So let's do this example right here. So let's say we want to take the integral of cosine cubed 2x sine to the 5th 2x dx, right? Now what do we see? We see that both of them have odd powers. So what does the rule say? It says if both have odd powers, just pick one method. So let's actually just pick one method, right? So let's say since right now cosine is the lowest power, and we can use cosine. We can use the cosine method, right? We can use this method right here. So let's rearrange this integral first. So we want a power of 2 for cosine. So cosine squared 2x sine to the 5th 2x, and then we pull out one of the cosines. We strip one of the cosines off of a cosine cubed, so we have cosine x dx. So we're gonna try to make everything we're gonna try to make everything into sine, right? We're gonna try to make everything into sine. So the first step would be using the Pythagorean identity, right, for this part. So we know this is just gonna be 1 minus sine squared 2x times sine to the 5th 2x and times cosine x dx. Now, you see why I didn't change this cosine x? We're gonna need that because after we make everything in terms of sine, we're gonna use u substitution now. And since we already know that from our derivative rules that the integral of sine is cosine. So we're gonna be substituting u as sine 2x, right? Since we have a 2, the angle here is 2x. So u is equal to sine 2x. The derivative of this is simply 2 cosine 2x, right? And we have this cosine 2x like right here. All we need to do is add a 2. And so all we need to add is a 2, right? So we can do that. Just add a 2 right here. Add a 2 and add a 1/2 outside. So in the final integral or final solution, the 2's cancel. So let's substitute now. So we're left with 1 minus u squared, right? Times, because this right here, sine squared 2x, is two of these. So it's just going to be 1 minus u squared. And then right here, we have sine to the 5th 2x. So we write u to the 5th du. And then du, we know is 2 cosine 2x. And we made that right here. We did that right there. Oh, I forgot the 2x over here. This is supposed to be 2x, not x. This as well. That's not x, this is 2x. So now that we have everything substituted, now we can continue with our integration. And there's a 1/2 outside too. So now we can continue with our integration. First step is going to be distribute this u to the 5th. And we end up with u to the 5th minus u to the 7th du. Now, if you want to, you can separate the integral. So let's do that. U to the 5th du minus u to the 7th du. Now, once we do that, we can easily integrate now. This is just a regular power rule. This is one of my favorite rules. So, and this is one of the easiest rules. So it's going to be u to the 6th over 6th minus u to the 7th over 7th. Oh, actually u to the 8th over 8th. U to the 8th over 8th. Now, you can substitute back in sine. because we know u is equal to sine 2x, so just substitute back in sine 2x. So sine to the 6th 2x over 6 minus sine to the 8th 2x over 8. And the final step would just be distribute that 1/2. And we get the final answer of sine 6 2x over 12 minus sine to the 8 2x over 16 plus c. Remember that plus c, this is an indefinite integral. And there you go. That is our final answer using trig integrals. So for the next case, it's similar to sine and cosine, but we're going to be using tangent instead. So I'm gonna put these two cases together because they have similar rules. So let's say if it's so that or so either of those forms, right? So once again, there's gonna be we have to know if it's odd or even, right? So if you have odd powers, we're gonna use the actually for this one, we're gonna be using Pythagorean identities all throughout. No half angle identities. The half angle identities only apply to integrals of this form, right? For everything else, we're gonna be using straight up the Pythagorean identities. But we have to use the Pythagorean identities for tangent and secant squared and cotangent and cosecant squared. So we're just going to use Pythagorean identities all throughout. So let's say for this first case, let's split this into A and B. So for A, if power of tangent is odd, we keep one factor of secant x tan x, secant x tan x, and use the Pythagorean identity. So I'm just gonna write Pyth identity, and this identity is for tangent squared x. So tangent squared x is equal to secant squared x minus 1. So this is the Pythagorean identity we're gonna have to use. So whenever you see tangent is odd, the power is odd, keep one factor of tangent x, secant x, and then use the Pythagorean identity. So you want to make sure we get at least a square for tangent, so we can substitute and make everything in terms of secant. Now for B, actually for A, there's another part to it. Say if the power of secant is even. Now when we have this, what we want to do is actually strip off. So whenever we have even powers for secant squared, secant for secant in this form of integral, we want to strip off a secant squared x and use, so whenever we have a secant squared, so it has to be at least a power of equal to 2 or above, right? So like 2, 4, 6, 8, 10, 12, so on. So we need a power like that in order to do this. So whenever you see the secant is a power of like 2 or any other even number above 2, then we can use this method where we strip off secant squared x and use the Pythagorean identity. Secant squared x is equal to tangent squared x plus 1. And we specifically strip off secant squared because the derivative of tangent is secant squared. And in this method, we're going to be using tangent as our u when we're solving for the integral. So and another part, just like I said, we're going to be using u. U would be tangent in this second part of the statement. The rule for tangent in the first part, right? We said that we're going to be using this identity, and we're doing this so we can make everything in terms of secant. And in this case, we're going to be turning we're going to be setting u equal to secant and then solving. So there's a lot of methods you could do in trig integrals. The good thing about trig is that it's very like diverse, and there's a lot of different ways you can get to the same answer, and all of those ways are correct. Like there's a few ways to get the same answer whenever a trig is involved. So that's the good thing about like trig sub and trigonometric integrals. So this is part A, right? This is this case A. Now for case B, let's take that down here. Like that. Let's take that down here. So for case B, if the power of cotangent is odd, we keep one factor of cosecant x, cotangent x, and use the Pythagorean identity cotangent squared x is equal to cosecant squared x minus 1. So this is the Pythagorean identity we use for when cotangent has a power that is odd. And this is for case B. If power of cosecant x is even. Now when cosecant x is even, now we have to strip off a cosecant squared x and use the Pythagorean identity cosecant squared x is equal to cotangent squared x plus 1. So this is what you can use. And you see why I grouped them together. It's because the rules are very similar. We're just using different trig functions. So let's do like an example for tangent secant x, tangent x, secant x, and then let's do an example for cotangent x, cosecant x. So examples. Our first integral we're going to do, let's try to find the integral of tangent to the 5th x, secant x to the 5th dx, right? Let's do this one. So no, not to the 5th, to the 3rd. So what are we gonna do here now? So if you look back at the rules, right, it says that if the power of tangent is odd, keep one factor of secant x tan x, and use the Pythagorean identity tangent squared x equals secant squared x minus 1. So let's use that method, right? Let's use that method since we see that tangent here has a power of 5, and 5 is an odd number. So let's do that. Let's strip off, not even strip off, let's keep one factor of secant x tan x, and make sure we have at least a tangent squared we can work with. So first step, we take out a secant x tan x, right? We factor out a secant x tan x, and we're left with tangent to the fifth x, tangent to the fourth x actually, because we take out one of the tangents, x, and then we get secant squared x, and this is going to be multiplied by secant x tan x dx, right? We factored out that secant x tan x. Now, when we look at this problem right now, we don't see a tan squared x just yet. So we need to actually rearrange this equation a little bit more so we're able to substitute the Pythagorean identity. So what we're going to have to do now, in order to make a tangent squared x, all we have to do is look at the tangent to the fourth x. This is simply, we could rewrite this simply as tangent squared x, right, squared, because if you square tangent squared x, you get this right here. So this is what we're going to rewrite it as, and then we're going to keep secant squared x the same way we want it, because we want everything in terms of secant. So we can set secant equal to u. So we have secant x tan x here dx. Now the next step is just set u equal to secant x, right? This is what we wanted, because once we get to u substitution, everything just simplifies itself. So the goal in trig integrals is to get to a point where you're able to do u substitution. So the derivative of secant x is just secant x tan x dx, and we have that like right here. So all we have to do now is do our before we even substitute, one thing we have to do is use the Pythagorean identity, right? Almost forgot about that. So tangent squared x is just secant squared x minus 1 squared secant squared x times secant x tan x dx. So this is what we end up with after we substitute the Pythagorean identity. Now we can use u substitution. Let's change everything into variables of u. So once we do that, so we get integral of u squared minus 1 squared times u squared, and then we just keep the secant x tan x dx the same way it is. Actually no, this is actually just du, so it's u squared du. So there we go. Now you see how simple that got? This is just going to be another problem where power rule is involved. So first thing we're going to do is just factor this out. Expand this binomial. So when we expand this binomial, we get u to the fourth minus 2u squared plus 1 times u squared du. We distribute this u squared, and we get u to the sixth minus 2u to the fourth plus u squared du. Now this is all power rule. Now we can just simply do our power rule and find our final integral. So I'm not even going to split this. I'm just going to do everything at once, because the splitting the integrals and doing all that is just going to take too much time. So let's just do this integral first. U to the sixth is just u to the seventh over 7. This right here, negative 2 to negative 2u to the fourth is just minus 2u to the fifth over 5. And u squared is just u cubed over 3. Now all we have to do for the final answer is make everything in back to whatever x was. So we want to change from u to x. So u to x, right? And we know we substituted u for secant x, so just substitute back in secant x. So we get secant 7x over 7 minus 2 secant to the fifth x over 5 plus secant cubed x over 3, and then the plus c. And that is our final answer for case A of this type of integral. Now let's do this type of integral. Let's do an example for cotangent x and cosecant x, right? So our second example is going to be right here. Integral of cotangent to the fifth x cosecant to the fifth x dx. Let's do that. So looking at the rules, it says that if the power of cotangent is odd, we keep one factor of cosecant x cotangent x and use the Pythagorean identity. So we see that the power here of cotangent is actually 5. So that's odd, so we use that method. So let's rearrange this equation. Let's pull out a cotangent x and cosecant x first. So when we pull that cotangent x, cosecant x out, we get cotangent to the fourth x, cosecant to the fourth x, times cosecant x, cotangent x, dx. So we pulled out that cosecant x, cotangent x. That was the first step. So the next step would be trying to so right now we have the same problem with the previously, where we had tangent to the 4x and there was no obvious second power of tangent. So what we have to do is rearrange this equation a little so that we have something that's at least gives us cotangent squared x, so we're able to substitute the Pythagorean identity. So let's rearrange this equation a little bit more, like similar to what we did with the previous example. So let's do cotangent squared x squared, right? Because if you square this, you're just going to get this. So let's just rewrite it a little like that. So we have this cotangent squared x, like write it right there. So the rest of the problem stays the same. So now that we have the cotangent squared x, substitute in the Pythagorean identity. Squared so this is what we get so far. So we substituted in the Pythagorean identity, and now we're ready for u substitution. So let's substitute in cosecant for u, right? Because we made everything in terms of cosecant. So u is equal to cosecant x, and then du is just cosecant x cotangent x dx, and that's perfect because we have that right there. Now we can switch to terms of u. So it's going to be u squared minus 1 squared times u to the fourth. Oh wait, I think there should also be a negative sign here. This is the derivative of cosecant x cotangent x is actually negative cosecant x cotangent x. So let's actually just use that rule we did. Just add in the negative and just put a negative outside so the negatives cancel in the final answer. So now we're ready for, so we just have to add a negative outside. That's the only thing I missed. So we can continue with the u, substituting for u, and we end up with this, right? So du is right here. This is u to the fourth. This right here is u squared minus 1 squared. And we just have this negative sign because we needed to add it here. So let's continue. We do basic distributive property here. Actually, not even distributive property. First you expand the binomial, then distribute. So let's expand the binomial. This is going to be u to the fourth minus 2u squared plus 1 times u to the fourth du. Now you do the distributive property. And we get u to the eighth minus 2u to the sixth plus u to the fourth du. Now once we get up to this part, this is normal power rule, and you just solve. So let's find the integrals of this. So this right here, the integral of u to the eighth is just u to the ninth over 9 minus 2 u to the integral of 2u to the sixth is just 2u to 7th over 7. Integral of u to the fourth is u to the 5th over 5. And then all we have to do is substitute back in cosecant. So we have to go from u to x, and when we do that, we get cosecant to the 9x over 9 minus 2u 2 cosecant 7x over 7 plus cosecant to the 5th x over 5 plus c. And if you want to distribute the negative sign, you can do that. I'm just not going to distribute it and just say this is the final answer. And that's basically how you do trig integrals. So just a little review. For trig integrals, there are 3 kinds of forms. One is with sine and cosine. One is with tangent and secant, and one is with cotangent